What's up, everyone? So it's been a long time for me from doing geometry or trigonometry problems. If I remember correctly, the last time that I made a video about a trigonometric problem is roughly saying like 2-3 months ago. So today we're going to talk about the following problem. We're going to prove that pi is greater than 3.05, and this problem is very easy to understand what the question is asking about, but it's actually a little bit challenging to give a solution because we need to prove it. And this problem is actually from 2003 Tokyo University entrance exam. You perhaps can find some videos about the proof of this problem, but they're mainly in Japanese because those are Japanese math teachers, and this problem is also from one of the universities in Japan. So this time I try to kind of like do a translation of it and well, use pretty much the same method as what they do, but I'll explain step by step. So before we start, let's notice that since we want to actually prove pi to be greater than some numerical value, here we're not allowing to use the numerical definition of pi, so we pretend that we don't know that 3 is approximately 3.14 whatever, or like in some fractions, or even like an infinite sum, like 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus so on and so forth. Don't do that. The only thing that we can assume is we only know the geometric definition of pi, meaning what is defined as pi, which I bet everyone knows already. Pi is called is a special value for circles that we use for such as for circumference or area. So in fact, we would define pi as the ratio between the circumference of a circle and its diameter. So that's how we define it in geometry. And that is the only thing that we know of. We don't know about any numerical value or some algebraic results that can generate pi for us, okay? So based off of the condition that we have, now we're trying to prove that pi is greater than 3.05. So before we move on to the actual proof, you can pause the video and think about it yourself and see if you actually get the idea of the proof that's similar to mine. Also, don't forget to like and subscribe my channel so that you can also check out my other videos, and also turn on the notification so that if whenever I have new videos, you won't miss it either. Okay, are you ready for it? Let's jump into the solution. So before I actually get to the solution right away, I'll give some hints. Since we know that pi is defined as the ratio of a circle, more precisely, it's a ratio between the circumference and the diameter of a circle, I'm going to draw a circle first, like this. So just pretend it is a perfect circle. Then we say that pi is a ratio, so we know that, well, or by definition, pi is equal to the circumference over the diameter, or known as 2 times of the radius. Good. So let's call this point right here the center of the circle. Then from the center of the circle to anywhere of the circle or the edge of the circle, the distance is what we call the radius, and we know that the distance is always the same. Good, let's call it R here. And then of course the circumference will be C. Okay. Now what can we do to this on this figure? We're going to do the following. So as a hint, we're going to trying to show that pi is greater than some value. So geometrically, we can try to do the following like this. So first, we're going to start with a triangle, and later on we'll use other polynomials as well, but not polynomials, polygons. And it doesn't really matter the shape of the polygons as long as they're convex, meaning that all the vertices are actually are pointing outside, and of course we wanted all the vertices to be on the circle. And in fact, it doesn't really matter, but for us to easier to understand, and also easier for our calculation, we will just make all the polygons that we later on going to draw on this circle be regular, meaning that they the length of each side or each edge of the regular polygon is the same. And of course it means that the angles of the polygons are also the same, so that it will be easier for us on our calculation. Now if we first start with a three side, which is a triangle, we of course can tell that from the figure, the perimeter, meaning that the total sum of the length or of the side of the triangle is smaller than the circle, because we can see that we have a straight line here, here, and here to make out the triangle, and then we have a circle that actually covers outside, and we know that the shortest distance between 2 points is a straight line. So for a circle, it's not a straight line, and we call that an arc. So each arc is actually longer than the edge of the triangle. Good. So here is what we're going to do. After we draw the right triangle, of course we know that from the center of the right triangle to the to each of the edge, each of the vertex is equal to r, the same as the radius. And we can just now divide up the right triangle into three congruent triangles like this. And we of course see that they're congruent because they just split the angles into two equal halves. And you can just use a lot of, some basic geometry ideas to show that they're all congruent. Now, what is the angle, or what's the small angle right here? We know that the sum is total for these two angles, and these two are evenly distributed or evenly divided. So it means that each angle will be half of 60 degrees, which is 30 degrees, or you can, I will stick with 30 degrees here so that we won't get confused with the pi that we're trying to find. Good. So now we can try to find out the length of we can try to find the length of the regular triangle, and then we will just multiply it by 3 to get the perimeter of the right triangle. Not the right triangle, the regular triangle. So what can we do? Well, we're going to do this. We're now going to extend this vertical line, and then we'll get a right angle here, of course, so that now we have a right triangle with 30, 60, 90 degrees. And in this case, we know that the hypotenuse is equal to the radius r. So this leg right here is, of course, half of the hypotenuse by Pythagorean theorem. And we can now get the length of this half of the base, which is radical 3 over 2 times r, meaning that if we double it, we'll get the base of the triangle equals radical 3 times the radius. Okay. Then again, we now see that the perimeter of the right triangle would then be 3 times of the base, which is 3 times radical 3 times r. Then what are we going to do? Now we're going to substitute back in. Since we know that we always get the circumference, which is the perimeter of circle, is always greater than the perimeter of the regular polygon that we're drawing inside of the circle. Well, from the figure, we now can do the proof. Use the definition here. We have pi is equal to c, the circumference, over 2r. Now we use the concept that the circumference is always greater than the perimeter of the polygon, the regular polygon we're going to draw. We see that this is always greater than p over 2r. And again, r is a positive number, so it doesn't matter what we're dividing by. If c is greater than p, we divide both sides by some positive number, the inequality doesn't change. So we now get the following. And from the graph, from the figure, we say that the perimeter that we have is the perimeter of a regular triangle. So we will end up with 3 radical 3 times r as the perimeter over 2r. So we see that it doesn't really matter what the radius is, and they'll cancel out because we're taking the ratio. So we get 3 radical 3 over 2, like this. Good. So how do we show that? Well, now we need to know some of the values. So we have to know the following. Radical 2 is roughly 1 point. Well, I'm going to do it this way. Radical 2 is actually between 1.4142 and 1.4143. So you can actually check using your calculator to see that the few digits after the decimal of radical 2 is 4142, and then something later on. Yeah, something non-zero later on. Then for radical 3, we're going to do the 3205, something like that. So it means that this number is in between 1.7320 and 1.7321. Again, is it necessary to put that many digits? Not really. We can just take the next 2 digits, but just to make sure that we get our accuracy, it's better to use more digits so that we can we can lower our error. Okay, so here we already know the value of radical 3, so we're going to check. So now we need our calculator. We don't really need our calculator. We see that radical 3 is smaller than this value, so we're going to do a scratch work aside to show that radical 3 times 3 divided by 2 or times 1.75, hopefully it will be greater than this value. And if we have that, we're done. So let's see, 1.5. Because again, what we're trying to do is, this is what we call analysis. So we're trying to depend on the question. Here we would like to take the upper bound, so that we will see that if the upper bound is still smaller than this value, then we will guarantee that this is great. Well, how should I say? If we can guarantee that the upper bound value is bigger than this by a bit, then we can bigger than this value, then we can guarantee that pi is greater than the upper bound, which is greater than this value. So we can somehow assume that the value that we get is in between these two values. Okay, good. So let's see what we'll get. If we do our calculation, we will actually end up with the following. So I'm actually doing it with my bare hand, so let's see what we will get. So we actually end up with this value right here, 2.59, which is clearly smaller than this. So we proved that pi is greater than this value, which is greater than this. Well, actually, this value is less than this. And it is also less than, of course, something that we want to prove. So what does that mean? It means that we don't have enough information to tell that whether pi is still greater than this or not. Because now we actually can consider it this way. We have pi is greater than this a value, which is, is greater than this a value, which is less than this upper bound of a value. Let's call b, which is less than c. Okay, so we can see that a is less than c, but then pi is greater than a, and a is less than c. So we have the problem that we know a is the smallest. Okay, this a value is the smallest, but we don't know whether the c value and pi and the actual value of pi, which one is bigger. We don't know the order of it because of here. We want to, in order to prove that, we want to get greater than every time. So what we're going to do is, later on, we want to try to take the lower bound instead and show that each time when we take a lower bound, that lower bound is still bigger than this number, so that the number pi is actually on top, and then every time we're trying to get lower and lower, and that smaller value is still bigger than what we want to prove. But here is the idea of how to prove this problem. Okay, and of course we are not done yet, so I'm going to write down the actual proof in the next video, and until then I'll let you guys think about what polygon we should take, or how many sides do we need at least in order to prove this problem or this inequality. All right, I'll see you guys tomorrow.